Today we are going to talk about how to generate femtosecond pulses of different wavelengths for applications like pump probe spectroscopy. As we have talked about the amplifiers earlier, the reason why we want to use amplifiers is that for many applications you want to use a laser pulse that is really very intense. And the way you do it, as we have discussed, is first you use a seed laser, an oscillator, you feed it into another laser which is an amplifier, and we have learned different techniques of elongating the laser pulse, feeding it into the cavity of amplifier by using Pockels cell, then switching it out using another Pockels cell or maybe the same Pockels cell, and then compressing it once again to get an amplified pulse which is short as well. Now, the issue with this sharp pulse amplification method that we have discussed earlier is that you can only get one modal wavelength. Of course, we know that femtosecond pulse by itself is broadband, we are not talking about that. But if you think of the modal wavelength, there is no way in which you can tune it, because the seed pulse has to have exactly the same frequency as the one that will come out. Well, when I say frequency, I mean modal frequency, as the one that will come out of the amplifier. So, if you try to tune the seed, then you have to play around with the amplifier laser cavity and all that, and then alignment becomes problematic. I am not saying that tunable amplifiers are not there, they are there, but alignment there is a non-trivial process. So, what one needs to do is one needs to work on the pulses post production if you want to generate pulses with different central frequencies. And the way it is done is called optical parametric generation and optical parametric amplification. So, these once again are nonlinear optical techniques, and as we are going to see, they are exactly the opposite of what we have studied earlier, second harmonic generation and some frequency generation to be more general. So, as you know, in some frequency generation what we do is we take light of two different frequencies, and we have in our previous discussion we have developed this concept of signal and idler. We have talked about the relative frequencies of signal, idler and pump, and there what we said is that the pump is the highest frequency, right. The pulse with highest frequency is called the pump pulse, and that time it might have sounded a little counterintuitive, because there you are actually producing the pump. But when we say pump, we think of something that is going in, right. The reason why we introduced it at that time is what we are going to use now. So, earlier we have studied some frequency generation, not very difficult to understand, by considering virtual states. We said it is sort of like two droplets of water joining up to giving you a droplet of bigger mass. Similarly, you have two photons of smaller energy which join up to give you a single photon of a higher energy. And what we explained was that you have this material in ground state, then let us say omega s comes in, the signal frequency, the system gets promoted to a virtual state, and then at the same instant if omega I comes in, it will get promoted to higher virtual state, frequency of the energy gap between which and the ground state would be say h omega p, where omega p equal to omega I plus omega s. And then when, since it is a virtual state, it has 0 lifetime. So, when relaxation takes place within 0 lifetime, the light that comes out has frequency of omega p, which is omega s plus omega I, and that is not very difficult to understand, right. Omega s plus omega I combining to give you omega p. What we want to talk about now is whether it is possible to do the reverse. We have omega p, which is a higher frequency. Is it possible to break it down into two photons, one with frequency omega p, omega s, and another with frequency omega I? And the answer is yes, but this is not as efficient a process as its inverse. it is much easier to combine omega I and omega s to give you omega p than to take omega p and break it down into omega s and omega I. That is point number 1. And we are not going to get into the detailed quantitative treatment of this, that itself can be a course. But what we are trying to do here is that we are trying to develop the general idea of how this is done. Now, can you, just looking at this expression, does it occur to you that there is a potential problem or potential issue or potential feature associated with breaking up omega p into omega s and omega I? That problem is not there when you start with omega s and omega I and produce omega p, which is a sum of their frequencies. When I want to break down into constituents, there is something that should strike us. What is that feature I am thinking about? See, when we do some frequency, you start with omega s and omega I, there some can be only one quantity, there is no problem with that. But you start with omega p, there can be in principle infinite combinations of omega s and omega I, right. So, there is no predetermined value, at least at this moment. We will see later on whether it is possible to bring in some predetermined value. But as of now, all that is required is omega p must be omega s plus omega I, right. So, that reminds me of a story that I read as a child, that there was an arithmetic problem in which it was said that 10 pence cost 50 rupees, how much does 1 pen cost? And a student wrote, we cannot say. And when he was asked why you cannot say, he said, see, I mean, nowhere is it written that they all cost the same. So, I can buy 1 pen for 5 rupees, 1 pen for 10 rupees and have some kind of a combination, and there are many different combinations that are possible. So, actually that student was right. So, you have to say that each pen costs the same. Here we cannot say each pen costs the same, okay? Or maybe we can, as we will see later, right. But this is what it is. Now, this thing takes place and it is actually a complicated process. When you produce these photons, they are correlated, and the science of this goes beyond our requirement of producing light of different frequencies. Actually, what you produce here is correlated photons, and that opens up a different branch altogether. In our institute, we had this talk by Professor Mukamel couple of weeks ago. You might remember that he did mention in the passing correlated photons, right. So, this is where it starts. Now, when you do it, let us say we can do it, that a pump light gets into a nonlinear crystal and gets broken up into signal and idler. First thing that we want to say is, you cannot have infinite combinations. A little while ago we said, at least at that point, I could write any value of omega s, any value of omega I, as long as they add up to omega p. That is not necessarily correct, because not only do you need energy conservation, momentum has to be conserved as well, as we had discussed for some frequency generation. The moment you say momentum has to be conserved, the number of possibilities goes down, right. Yeah. And also directionality has a role to play now, because it is just splitting. Now, I can combine this k s and k I, and the vector sum can be k pump, but you can see that if I have a longer case going higher up and I have a longer k I, then again you can have the same vector sum, right, if you change the angle. So, once again it is going to depend on the angle at which the photons propagate, right. And for a completely collinear geometry, the equation that you get is, once again you might remember that we had discussed that those polar plots and all, and we said that the condition for production of second harmonic was that the refractive indices had to match for the fundamental and second harmonic. Here also refractive index multiplied by omega p, Np multiplied by omega p equal to Ns multiplied by omega s plus Ni multiplied by omega I is the conservation of momentum condition. The moment you bring this in, it is sort of bringing in quantization, right. Not all combinations of omega s and omega I are going to be now allowed, but still there will be many, okay. There can be many. Of course, we have already brought in some restriction here, remember we are talking about collinear geometry, that is what will restrict things a little bit. Now, why am I not saying that there will be only one combination? Why am I still saying that there can be several combinations? Np omega p equal to Ns omega s plus Ni omega I. So, if Np is defined, Ns is defined, Ni is defined, then I should think that only one pair of values of omega s and omega I should satisfy this condition. Why am I still saying there can be several pairs? Yes? Yeah? What do they depend upon? Ns and Ni are not constant, that is the answer, even Np may not be constant. What would they depend upon? Sorry? No, wavelength is frequency, right? Omega I, omega p, they automatically wavelengths are defined, it cannot be wavelength. Something else, something simpler, something you studied when you were younger, before you studied wavelength. Yeah? Yes, maybe, but then I am working with the same medium. I will not change the medium. So, that is one way, of course, you change the crystal, you can have different kind of optical parametric generation. Suppose I work with the same medium, what can I change to change the refractive indices? What about temperature? Yeah, temperature. So, you can have temperature controlled refractive index. So, therefore, changing temperature, as we are going to demonstrate later on, you can actually get different combinations of omega s and omega I. Okay. So, temperature tuning becomes very important here, right. Okay. So, this would be the simplest geometry in this case. So, what we have here is we have this omega p coming in focused onto Z1, and then here we have the nonlinear crystal. Okay. Here is the optic axis. Let us say we do not know what omega I and omega s are at the moment, we only know omega p, but let us say they have been produced. So, what do you have? You have a mixture of omega s, omega I, omega p. Okay. And now, suppose you want to take the idler out. Idler is typically the lowest frequency. Lowest frequency means longest wavelength or shortest wavelength? Longest wavelength. So, use a long pass filter. If you use a long pass filter, you can choose to get only the idler out, or you could use a long pass filter which will allow the idler as well as the signal to go out. And then by using a dichroic mirror, you can get the idler as well as the signal going in different paths. That is what is done in a commercial OPO or OPA. Okay. You can actually generate both. I mean, you will generate everything, but you can actually use both if you want. What is the problem? The problem is intensity, very, very small. So, first of all, what you can do is, like earlier, you can do angle tuning for phase matching. That way you can decide omega s, omega I, and you can optimize the conditions by which they come out. This we have to remember that signals are very, very low. See, even some frequency we said typical efficiency is like 20%. Here typical efficiency would be 2% perhaps, or 1% or less, depending on what kind of material it is, very low. And then depending on the NLO material, you can have type 1 phase matching or type 2 phase matching. Type 1, type 2 phase matching we have discussed in the previous modules. Now, what is the application? The major application in this case is, what is the range that is available to us most easily? What is the range of wavelengths that is available to us? Suppose you are using a Tie-Sapphire laser. The range of wavelength that is available to us very easily is red, right. From red, we have learned how to create blue or even UV by second or third harmonic generation. Here, we have learned how to create IR, right, and also how to create single photons. So, one application that we are not really going to talk about here today, but it is a very important application of optical parametric generation is that many times you want to do experiments in which you generate only one photon. That is done very easily here. Okay? You can do it by angle tuning, you can do it by modulation of intensity and all that. You do it in such a way that at an instant only one photon is produced, and then you do whatever you want to do with it. Okay? Do you know what is a very good detector for a single photon? Yeah? Yes? Our eye. Our eye can actually see a single photon. If you are in a dark room and one photon comes in and it is, if it impinges on your eye, that will generate a signal. Eye is good enough. Right. Now, let me show you the schematics of construction of an optical parametric oscillator. Where does this oscillation thing comes? We have a later slide where the schematic of oscillation is shown briefly. See, we have said that the efficiency is very less, right. So, if efficiency is less, how do you increase the efficiency? One is by amplification, which we will study later. The other is if you make sort of a laser cavity, and if you make the signal beam go around in the cavity several round trips, then you can have some amplification, right. So, and note the date. Physical review, let us find what which year was this published? 1965. So, these experiments started more or less along with the invention of laser. The moment lasers were invented, people started thinking what can you do with them. Perhaps I do not know whether they even thought that we are going to do pump spectroscopy and all that at that time. They just wanted to create single photon, they wanted to create correlated photon pairs, they wanted to have a mean of tuning the wavelength. So, as far back as 1965, before any of us here were born, this thing was there. Okay. And here is the schematic. Again, the active medium here is neodymium ion, the different substrate. It gives you 1058 nanometer, 1.058 micron, that is, let us say omega 0. So, what they did was, first of all, they put in a lithium niobidate crystal, they called it T1 crystal, and the work of this crystal is actually to do what we already know, to generate the second harmonic 2 omega 0. Now, the moment you create second harmonic, you know very well that the efficiency of conversion is only 20% or 15%, 10%, 8%, something like that. So, there you have two wavelengths already, omega 0 and 2 omega 0. Which one is omega p, which one is omega s? How have we defined it? What is the highest frequency? What is the largest frequency? What is it called? Pump signal or idler? No, highest frequency. Highest frequency is a pump. So, this 2 omega 0 is actually equal to omega p, that is your pump, and omega 0 is the signal. Of course, in this case idler will also have frequency omega 0, if you are going to use it like that. So, then here after that they had this infrared absorbing filter. Which one will get removed? Omega 0 is gone, you only have 2 omega 0 here, omega p. Okay. Then they had this second lithium niobidate crystal T2, from which you are going to generate omega s and omega I. Okay. How can you do it? We have discussed already that if you change temperature, then all these refractive indices will change. So, even for collinear geometry, you can get different frequencies for idler, different frequencies for signal, if you simply change the temperature, and that is the experiment they actually did. Unfortunately, the 1965, many years ago. So, that time drawing graphs and all perhaps did not capture so much of attention like what we do nowadays, but you can see what is there on the x axis, what is there on the y axis. X axis is temperature, degrees centigrade, right, and it goes from 46 degrees to 66 degrees, about 20 degrees. And y axis, what is y axis? Yeah, it is wavelength in micron. Okay. So, what you get is you get two branches. You see these dots, these are the experimental points. The two branches, this one is the signal, this one is the idler. Is that right? Did I say the right thing? Why not? Idler is longer wavelength. Look at the y axis, shorter values on the top, longer values at the bottom. The top one is 0.96 micron, then this is 0.98, 1, and the lowest one is 1.16. In 1965, people used to think differently, what can I do? So, what they have done is, they have plotted from the lowest value of wavelength is on the top, or you can think like this, they have written wavelength, that is the issue. Highest value of frequency is on the top, right. So, in this parabola that we have, the points on the top are the signal, points at the bottom are the idler. Okay. And many times you see there are more points, I do not know if you can see that. You see there are more points in the top than in the bottom. So, many times they could not even detect the idler. The idler got absorbed or intensity was too small, they could not detect, something like that. Signal is a little better, that is why it is called the signal. Okay. Lower the frequency, more difficult it is to detect. Okay. I have no idea why it is called idler of all things, because I mean it is as idle as the signal, I guess, but signal is a little easier to observe. Okay. So, by changing the wavelength, changing the temperature here, different omega s and omega I were prepared. Of course, you understand that for a particular value of omega s, frequency of the signal, frequency of the idler gets automatically determined, right, because frequency of pump is known, that is 2 omega 0, 1058 multiplied by 2 in nanometer, right. That is of course wavelength, the frequency corresponding to that. So, at a particular temperature you get omega p is the same at all temperatures, omega s and omega I values vary, with the condition that omega s plus omega I is always equal to omega p, that is 2 omega 0. Next, they had this silicon filter which cuts out visible light, and only omega s and omega I are transmitted. Okay. So, this is one of the first examples of optical parametric oscillator. I have not shown the entire diagram here, the entire diagram would look something like this, where this nonlinear crystal is actually put inside sort of a laser cavity, so that the resonant signal beam gets amplified a little bit, and signal and idler output typically travel in the same direction, and then you can further separate them by using no, that is not, that is in the next one, by using a using separation optics like dichroic mirrors. Okay. So, the problem is that the intensity is very small. So, when intensity is very small, you want to amplify it, and that brings us to the principle of optical parametric amplifier. And when we discuss optical parametric amplifier, actually two phenomena come to my mind when we discuss this. One is Raman effect, the other is stimulated emission, and you see why I am saying this. So, what you see in this diagram here is you have a stationary state, ground state, and you have a virtual state at higher energy compared to the ground state. Okay. Let us say that the pump frequency promotes the system to this excited to this virtual state. Okay. So, omega p takes the system to this virtual state here. Now, let us say, and that is why this reminds me of stimulated emission, let us say by some means I already have a little bit of omega s in the system. Okay. Now, what will happen? Sort of stimulated emission. Okay. So, if it sort of stimulated emission would take the system from this higher energy virtual state to a lower energy virtual state, difference in energies between which would correspond to the frequency omega s, right. So, this is what you would get, instead of 1 now you get 2 photons, the photon that perturb the virtual state with higher energy and the photon that is generated as a result of lowering the energy from the higher to lower energy virtual states. This is why it reminds me of stimulated emission, and you can see where amplification comes in here, right. One pump photon, one signal photon came in and 2 were produced, right. Now, what happens to the remaining energy? Omega p minus omega s, what would that be equal to? Omega I, idler, that would also come out automatically, right. This is how, this is the very basic principle of optical parametric amplifier. Now, if you think practically, where will we get omega s from? And then I want a tunable source, right. So, I might want as many possible values of omega s as possible. The best way of trying to do that is to generate white light. Yeah. Now, we are familiar with this concept of the white light generation. We know that if we focus an intense femtosecond pulse on a substrate like calcium fluoride or your sapphire, earlier experiments were done by focusing picosecond pulse on water D2O mixtures. Then you get something called self phase modulation and white light is generated. Of course, white light intensity will be nothing compared to the laser light, but we do not need a high intensity. We only need some photons that are going to cause this downward transition. So, a good strategy of building an OPA would be you take your light, laser light, say 800 nanometer light out of an amplifier, tisapphire amplifier, split it into 2 parts. Focus one part onto some substrate there, sapphire filter, okay, generate white light. Okay. Then of course, you need optics to collimate the white light and all. Then on the nonlinear crystal, focus that white light and focus the residual part of the output of the amplifier. Now, what will happen? Output of the amplifier is going to serve as omega p. All the components of white light can in principle contribute, can act as omega s, but by angle tuning the crystal and of course, by maintaining some temperature, you can select preferentially which of these frequencies of white light is going to act as omega s, right. So, by angle tuning, that is what happens in an OPA. By angle tuning, you can select the signal frequency and the idler is generated anyway. Okay. So, you have actually generated 2 different colors already. Now, you decide whether you want to work with the signal or the idler. Generally, we prefer to work with signal. Sometimes due to some problematic combinations of optics and all, the signal may not be all that accessible, and if you are fortunate that the idler frequency, idler intensity is large enough, then you might actually end up working with the idler. That is point number 1. Point number 2 is sometimes you want to work with idler. When do you want to work with idler? What is the output of your tisapphire amplifier? 800 nanometer modal wavelength. So, that is red. What is the constitution of the white light? It is all visible, is not it? So, typically your omega s would be in the visible range. Suppose you want IR light, how will you get it? Using all this, if you want for some application, suppose you want to do an IR probe experiment, or suppose you want to do an IR pump IR probe experiment, something like that, 2D IR. Then the only hope of generating IR from this essentially visible light giving system is to work with the idler, right. So, the frequency of the idler is essentially the difference of frequencies of pump and signal, is not it. So, this process is called optical parametric amplification, OPA. It is also called difference frequency generation, DFG. Okay. So, what it essentially does is that if you have the right optics, then in fact it gives you tunability from anywhere to anywhere. So, what you could do and what is done in commercial amplifier, commercial OPAs, as we might discuss in the next module, is that first of all you have nonlinear crystals by which you do second harmonic generation. That gives you access to blue and maybe even UV. You do third harmonic generation, 800 by 3, how much is that? The magic numbers, you have to know 800 by 3. You can either do arithmetic quickly or you have to know 267, right, 266, that is a magic number, third harmonic. So, third harmonic, second harmonic, fourth harmonic, this when you are into lasers, these things will occur to you automatically. 1064 is a magic number, NDAG, fundamental, 532 second harmonic, then third harmonic of that, fourth harmonic of that, all these numbers will come to us automatically. So, on one hand, by higher harmonic generation, you can access UV, right, and not only that, you do not have to be restricted to only the harmonics. Now, you can do this and generate signal in blue or maybe even UV. On the other hand, if you use the fundamental of the amplifier 800 nanometer as omega p, then you can get things in red and the difference frequency can give you IR. So, that is why an optical parametric amplifier, a single optical parametric amplifier, which is properly equipped with the right crystals and right optics and in good shape, can give you tunability from 200 nanometer all the way to IR. That is the strength of this piece of instrument. Okay. And the principle, if you do not go into very deep of it, the qualitative discussion of the principle is quite simple. Okay. So, again this is an example of a of one stage of an OPA. Typically, OPAs would have several stages, but this is something that is there and this is from the usual textbook that we use. So, let us say this is omega p 1047 nanometer and this is omega s 1.1 to 1.8 micrometer. Actually 1.1 micrometer means how many nanometer? 1100 nanometer. So, first of all I do not understand why this is 1047 nanometer and why that is 1.1 micrometer. I do not know, but we should not think that this is 1000 that is 1. That is why I wanted to make this. So, here in this system that we are discussing, actually your pump and signal have not very different energies. Now, the thing to note is the difference in polarization and that has a role to play later. The pump is vertically polarized, the signal is horizontally polarized. Okay. And the idler you will produce, you are using lithium niobate. If you remember what we discussed in the earlier ones, in LiNBO3 we have EOO kind of situation, if you take pump, signal and idler. So, the idler that will be produced will have the same polarization as the signal, not the pump. So, you change the temperature, you angle tune it, do whatever you want until you get signal and idler, right. Signal and idler have the same polarization, pump has perpendicular polarization. Now, it is very easy to take the pump out, just use a polarizer. Here they have used a Rokon polarizer, you can look up what a Rokon polarizer is. It is basically the same as Wollaston polarizer, you have calcite or something which is cut into two and then joined again, the regular stuff that you have been studying in organic chemistry, rotational polarization, polarimeter, that kind of thing. So, first of all when you use a polarizer, the pump gets cut out and then depending on what you want the signal or you want the idler, you are going to use a filter. The filter that is shown here is a germanium filter which will allow the idler to go through the smallest energy and it will not let the signal to go through. Okay. you can always use a dichroic mirror to send the idler one way and the signal the other way. That way you have access to both. Okay. So, this is the principle of optical parametric generator and optical parametric amplifier. What we have in our lab is an OPA, not an OPO. OPOs generally operate at much higher frequencies, similar frequencies as your Ti-Sapphire oscillators. So, OPOs are very good for things like upconversion experiments, femtosecond upconversion, femtosecond optical gating, because they can give you a continually tunable range of wavelengths at high frequency 80 megahertz. That is what you need for your fog kind of experiments. But in pump probe generally one wants to use OPA because you need higher intensities, right, and OPAs once again they are limited by the frequency that goes in, and OPAs also have their own limitation. Not all OPAs can work at all frequencies. Typically you want to use an OPA which can work at the frequency of the output of the amplifier, which in our case is 1 kilohertz, right. So, typically OPAs are associated with higher intensities, higher number of photons I want to say. I do not want to say energy because we will get confused with h nu, higher number of photons let us say and lower frequencies, whereas OPOs are usually associated with lower number of photons, but higher rep rates. Okay. Both have their own advantage, both have their own applications and both are equally costly. Actually an OPO is I think more costly than OPA. As you know, amplifier of course is more costly than oscillator because it contains an oscillator, it has to cost more. But if you want an OPO, that is why you will see OPAs everywhere. OPOs are not all that common because OPOs are actually very expensive. And if you have a short enough pulse for a Ti-Sapphire oscillator with this sealed Ti-Sapphire oscillators that we now have and with continuous tunability, very often people do not care for OPO anymore, but in some applications it might be required. Okay. So, that is what I wanted to say about OPAs. In the next module we will briefly discuss the construction of the OPA that we use, and then we have discussed instruments for a long time. We want to discuss some actual experiments, classical experiments that have been done. We will next go on to two experiments. One is Amit Zuel's experiments that got him Nobel Prize in 1999. How much time does it take for a bond to break and how does a bond breaks? What he called snapshots of bond breaking. We will discuss that in a module. Then I want to talk about water a little bit, because water is my favorite subject, and in any case our life is based on water. So, two things, one is solvation dynamics in water, Graham Fleming's work. The other is how vibration energy is transferred from one mode to the other in associated water molecules. That is Eric Niebering's work, and perhaps we will stop this section with Eric Niebering's work on visible pump IR probe experiments. Then depending on how much time we have, I want to talk a little bit about pulse shaping and I want to talk about 2D experiments. If we get time, we will talk about terahertz experiments as well. And the purpose of this course is that we want to have an overview of all the kinds of different ultrafast experiments that chemists across the world are doing at the moment. We are not going to talk about attosecond experiments, because until now I believe that there is no chemistry in attosecond. It may be a little atrocious statement to make, but then after all the reason why I am saying this is that it takes hundreds of femtoseconds for a bond to break, and chemistry starts with bond breaking. So, faster than that there are interesting phenomena, there can be state to state dynamics, but at least in this course we are not going to talk about attosecond spectroscopy, because that requires a different level of understanding. But these are the experiments which we want to discuss, and while doing that we will have to come back to instrumentation a little bit after this, because I want to talk about pulse shaping, because many of you might end up in laboratories where you have to do pulse shaping. If you want to do a 2D experiment, pulse shaping becomes extremely important. So, we will talk about that a little bit. Okay. So much for today.